Okay, in this presentation we are going to look at random number generation. You are using a simulation to find the mean and variance of a random variable which has the following density function. F of x is equal to k divided by 1 plus the exponential of minus x, okay, where x is between 1 and minus 1 and 1, okay. So the first question asks us, determine the value of the constant k, which is the numerator of this expression here, okay? And then generate 5 pseudo-random numbers from this distribution based on these draws from the uniform distribution, okay? So we're going to draw 5 numbers from the uniform distribution, okay, which is the fundamental operation of random number generation. 0.017, 0.757, 0.848, 0.531, and then 0.321. Okay. Now, you have generated 1,000 such numbers and have found that the mean is, or the sum of these numbers is 165.681, and the square is 339.275. Use these statistics to find a 95% confidence interval for the mean of the distribution and a point estimate for the standard deviation. We'll come back to that shortly. Now, it's sort of a question like this here sort of throws you a bit because thinking, hang on, is this the same stuff as we might have done in previous statistics courses? Or is it something new that I've forgotten to study? Well, the answer is the first thing. It's actually just use the fundamentals. We'll come back to that one shortly, okay? In fact, a lot of this question is essentially using the fundamentals. So, anyway, let's look at part A. The probability distribution must integrate to 1, okay? So this is our PDF there, our probability density function, and this is all the key information there. That's the PDF, and those are our limits of integration, okay? So, what I'm going to do here is first off re-express this expression here. We have fx, and let that equal to k divided by 1 plus the exponential of minus x. So 1 over 1 plus the exponential of minus x, okay? Now, what we could do there is just sort of rearrange it so we can express it as the f of x equals k times the exponential of x divided by the exponential of x plus 1. Okay, so we just essentially rearrange it so that it looks like that. What we're doing there is multiplying above and below by the exponential of x, okay, which is a perfectly valid operation. Okay, now this just hopefully makes things a little bit simpler to operate. When we try and calculate it there, essentially this is what we have to do. Our integral should integrate to 1. It must integrate to 1. So essentially what we have to do here is evaluate k and, well, evaluate this expression here and then k, or derive k from that. So what we're going to do here is use integration by substitution. Let u equal to the exponential of x plus 1. Get the integration, differentiate that, okay. And then we get an expression there for du equals du, which is e to the x dx, okay? So essentially what we have here, this expression here, when we use our integration by substitution, we end up with the integral of 1 over u du, which is the log of u, okay? And that is the log of the exponential of x plus 1, okay? So essentially, just an important thing here, really, I'm sort of laboring the point a bit, but essentially the fundamentals are very important in this question. And here it's integration by substitution. Be ready to have that in your, to answering some questions like this. Likewise, integration by parts. Okay, that's the key takeaway from this. Anyway, what we have to do here is to solve that. So 1 equals k times the log of the exponential of x plus 1, evaluated from 1 to minus 1 or minus 1 to 1. Okay. Log of e to the 1 plus 1 minus log of the exponential of minus 1 plus 1. Essentially what we end up with there is k times 1.3132 minus 0.3132 ends up as 1. That means k is actually just equal to 1. Okay? Now, so what we have to do now, that's k found, k solved, k is equal to 1. So the cumulative distribution function is f of x, capital F of x, and this is the integral of our probability density function, which we now know to be 1 divided by 1 minus e to the minus x. Okay. And when we integrate that, we get log of the exponential of x plus 1 divided by log of e minus 1 plus x. E to the minus 1 plus 1. Okay. So, we let f of x equal to u. Okay. And that's that integral there. Okay. So u is equal to this expression here. Okay. Log of exponential of x plus 1 divided by the exponential of minus 1 plus 1. Okay, these are a bit tongue twistery. Now, essentially, this is the important bit here. This to this, I sort of skimmed through it a little bit, but it shouldn't be that difficult. Now, this is the key thing here with regard to random number generation. So this is what really should be new. Okay, so starting off with what we have here, what we need to do is make that expression in terms of x. So what we have here is an expression in terms of u, okay? But what we have to do is just rearrange that algorithmically, or algebraically, I should say, such that it becomes an expression in x, okay? So we have a logarithm here, so get the exponential of both sides, okay? So we have e to the power of u equals the exponential of e to the power of x plus 1 divided by e to the power of minus 1 plus 1. So essentially what we're going to do is cross multiply. So we have e to the u times e to the minus 1 plus 1, and that is equal to the exponential of x plus 1, e to the x plus 1 I should say. Okay. Subtract 1 from both sides. Okay. And then get the logarithm of that. Okay. It's not a particularly nice looking expression. It's awkward looking, let's be honest. But we have an expression there in terms of x. Okay. So this is our end result. Okay. Not exactly pretty. Okay. And you may check in case I made a typo. But overall, the basic scheme, in the basic scheme of things, these are how things are expected to proceed. Okay. Okay, I just fixed things there so everything is in shot. So, this is the set of 5 numbers that we have drawn from the uniform distribution. And essentially what I'm going to do here is use this algorithm stepwise on a piecewise basis. For example, get the exponential of those 5 numbers. 0.017, get the exponential of that, we get 1.017. Okay, then build it up, multiply that by the exponential of minus 1. Okay, that part there, that's a constant term. Okay, and then we subtract 1 from each of those. Okay, and then get the logarithm of those. Okay, so those are the 5 numbers that we are expected to generate. So these are 5 observations from this probability distribution which we are simulating. Okay, minus 0.938, 0.650, 0.786, 0.282, and minus 0.121. Just as a remark, it doesn't really come into it for this particular question, but let's just say in other questions it might come up that you have a 1 minus u in your expression, okay, in the equivalent of this, okay, there might be exponential of 1 minus u or something like that. It is legitimate and valid just to replace 1 minus u with u, or actually vice versa if it helps, replace u with 1 minus u because they're essentially the same distribution. Okay, so that's a thing you can do. It's not really relevant for this question, but it's just something that to remark upon, that is a valid step in creating these sort of expressions. Okay, now, so based on the statistics given, we have 1,000 observations. The sum is 165.681. 1,000 observations. That means that the mean is 0.166. We use this expression here to find the sample variance. That's just the standard deviation formula, or standard variance formula. Okay, work it out. We're given this number here, 339.275, and this number here, 165.681, and then we work it out to get a variance of 0.312, which means the standard deviation there is 0.599, and that means using the standard confidence interval formula, point estimate plus or minus the quantile times the standard error being the variance divided by the square root of n. I just spotted an error there. That should be 0.035. Okay, so 0.166 plus or minus 0.035. That gives us 0.131 and 0.201 as the lower and upper limit, respectively. So this last part was just straightforward use of the confidence interval formula and, statistics 101 material. Okay, we'll leave it there.